Okay, so we are talking about, I guess I ended last time by stating Zaslavsky's theorem for you. And so what I want to do is state it again and prove it. Okay? So, but maybe let's do an example. So let's say that you have an arrangement. Maybe it looks like this. These are the hyperplanes 1, 2, 3, and 4. Okay? So this is the arrangement A, and then we drew the intersection poset, right? And we saw that it looked like this. So we're basically looking at all the possible intersections of some of these things. And well, I did this slowly last time, so let me do it a little bit more quickly this time. So remember, each one of these nodes represents an intersection. Like this one is the intersection of hyperplane 2 and hyperplane 4, which is this line, right? And so on. So we did that. Then we computed the Möbius function. And we said that the way we do that is that we assign a red number to each node, and we want to have the property that when you stand at each node and add up all the numbers below it in the poset, you should get 0, except for the beginning 1. So here we get -1, here we get -1, here we get -1, here we get -1, and here we get 2, 1, 1, 1, and then -2. Okay. And finally, we defined the characteristic polynomial, and I told you that the way to do that was basically to add up the numbers row by row. So here you have a total sum of 1, here the sum is -4, here the sum is 5, and here the sum is -2. And we make a polynomial out of these, which is q cubed minus 4q squared plus 5q minus 2. Right? So from the arrangement, you get the lattice of flats. From the lattice of flats, or the intersection poset, you get the Möbius function. And from the Möbius function, you get this polynomial. Okay? So it looks like a kind of an arbitrary procedure, but then the nice theorem, which we're going to prove, is that if you want to know how many regions the arrangement has, then all you have to do is plug in -1. Except you might get the sign wrong, so you fix the sign by a -1 to the d. Okay? Which basically amounts to taking the absolute value so that the number is positive. And if you want the number of bounded regions, then you just want to plug in 1. And again, you might get the wrong sign, and the way to fix it is to do -1 to the rank of the arrangement. Okay? But again, those factors are not too important. You just take the absolute value, basically. So this is the theorem of Zaslavsky. maybe as a sanity check, what happens if we plug in -1 here? We're going to get -1, -4, -5, -2, which is 12, right? So this arrangement should have 12 regions, okay? And you're not really seeing them right now, but let's see them, okay? So for now, forget that you have hyperplane 4, and look only at 1, 2, and 3. So 1, 2, and 3 intersect in this kind of a spinning wheel, and we saw that that has 6 regions, right? There's 6 regions around 1, 2, and 3. And then hyperplane 4 kind of slices through everything and splits up each one of those into 2. So that has 12 regions, okay? And if you want the number of bounded regions, well, it's going to be plugging in 1, which is 1 minus 4 plus 5 minus 2, which is 0. And that makes sense because here none of the regions are bounded, okay? Okay. So let's prove this. Well, but maybe I should just remind you that of the two definitions we're using here. The Möbius function from the poset to the integers is defined by the property that if you add up the numbers less than or equal to x, you're going to get, most of the time you get 0, but you're going to get 1 if x is minimal. 0 otherwise. Okay? So this is saying put 1s in the bottom, and then below every point, if you look at the numbers below it, they have to add up to 0. Okay? That's how we define the Möbius function. And the characteristic polynomial is given by this procedure, but in a formula, it looks like this: sum over the flats in the lattice of flats of mu of the flat. And I realized that I had a typo last time. I have q to the dimension of the flat. And I think last time I wrote d minus dimension, so I meant dimension. So for example, here I have q cubed, q squared, q1, q to the 0, and that's because here I have the 3-dimensional space, here I have the 2-dimensional hyperplanes, the lines, and the point. Okay? So these are the two definitions. Okay. So I'm going to prove this theorem, and it's just going to take a little bit of work doing some computations. So first, let's prove our lemma. Which is the following. For any flat in the arrangement, I'm going to give a formula for mu of the flat. And what this is sum over subsets of the arrangement such that the intersection of the subset is F, and minus 1 to the size of the subset. So is this notation clear? A is my set of hyperplanes, and I'm considering subsets B with the property that when I intersect the hyperplanes in B, that gives me my flat F. Okay. So let's do an example so that you see how this works. For example, what is mu of this line here? Mu of, so example, the arrangement, that arrangement, and the flat 1, 2, 3. Okay? And so the flat is this vertical line. Okay? So then what you're supposed to do is you're supposed to tell me what are all the ways of expressing f as an intersection of hyperplanes in the arrangement. Okay? So how can we express f as an intersection of hyperplanes? Well, one way is 1, 2, and 3. So 1, 2, and 3, when you intersect them, we get f. But there's other possibilities, right? For example, if you intersect 1 and 2, you get f. If you intersect 2 and 3, you get f. And if you intersect 1 and 3, you get f. Okay? So 1 and 2, 2 and 3, and 1 and 3. And I think you'll agree that these are the only ways of obtaining f by intersecting hyperplanes in this collection. And so what this is saying is that mu of f is equal to minus 1 to the 3 coming from these three elements, plus minus 1 to the 2 coming from here, plus minus 1 to the 2 coming from here, plus minus 1 to the 2 coming from here, which is 2, and hopefully that matches what I had here. Yeah. So it's a non-recursive formula for mu, because mu is defined recursively. So it has the advantage of being not recursive, but it has the disadvantage that it's kind of messy. I mean, it's not so easy to do this in practice. But okay, it's a formula. So let's prove it. Well, what we're going to do is basically prove that that thing on the right-hand side, so maybe I'll call it, so let's give this thing, let's call it nu of f for now. Okay? And of course, what I want to prove is that nu is the same thing as mu. And the way that I'm going to do it is I'm going to show that nu has the same defining properties as mu. Okay? So show nu has the defining properties of mu. Okay? So for instance, if x is minimal, well, in this case, the minimal element is just the bottom element of the poset, which is R3 or RD in general, right? So what is nu of x? It's the number of ways of expressing the whole space as an intersection of hyperplanes. So how can you obtain the whole space as an intersection of hyperplanes? Well, the only way is if you don't have any hyperplanes, right? Because as soon as you throw in a hyperplane, you're going to lower the dimension. So here, what we get is just the summation. I mean, we just get one term, which is minus 1 to the size of the empty set, right? Which is minus 1 to the 0, which is 1. And so that means that nu of the bottom element is 1, okay? Which is good. That's what we want. Okay? Now, if x is not minimal, then I want to prove that the sum over y less than or equal to x of mu of nu of y is 0. Right? Well, so we don't know this yet. This is what I want to prove. So how am I going to do this? I think one thing that I should do is, because x and y represent elements of this poset, maybe I'm going to choose to call them F and G so that you remember that they're meant to be flats of the arrangement. Okay? So I'm just going to change the names here. Okay? So let's compute what this is. Nu of F is equal to that thing. So we get some I'm just plugging in, right? I'm not doing anything intelligent here. Okay?
Would that be B of G?
Yeah, thank you. Thank you. I'm fixing an F and I'm adding for the G's that are below. And so for the same reason, I should have the intersection of B equals G here. Right? Okay. Now, let's point something out here, which is that, remember, the way that the order works in this poset is that it reverses the inclusion. So G less than or equal to F in the poset means that G contains F as a subspace. So let me also switch this and write it like this, making sure that this looks curly enough that it doesn't look like a bigger than or equal to say, right? Okay. Okay. So then I'm saying sum over all the G's that contain F, and then I do this thing. So then what I get is summation over B, a subset of A, such that basically the intersection of B can be anything containing F. And so I can just write it like this. Okay? So I read it like this. Now, here I have an intersection of things containing F. An intersection of hyperplanes containing F. And that is equivalent to saying that each one of the hyperplanes contains F. That's what it means to be an intersection, right? So every B contains F. The intersection contains F if and only if every one of these guys contains F. Okay? Now, you see basically what I'm doing here is I'm considering subsets of A where every hyperplane in B contains F. So in other words, what I'm doing is just saying that B is a subset of the hyperplanes containing F. Right? That's equivalent to saying this. Maybe I'll call this A sub F, where A sub F means the set of hyperplanes containing F. Okay? And now, if you look at this, what are we doing here? We're summing over all the subsets of a set minus 1 to the size of that set. Okay? And if you look at this in the way that we like to look at subsets of a set now as a poset, okay, so here's the set A sub F, here's the empty set, and now I'm adding over all the subsets of AF. So this is the poset of subsets of AF, which we know is just the Boolean lattice of size of AF. Let's call it BK. Okay? So what I'm doing now is I'm adding -1 to the size. Okay? So basically I'm adding ones here, then I'm adding -1s here, then I'm adding ones here, then I'm adding -1s here, and so on. And so you see what I'm doing here is just saying k choose 0 minus k choose 1 plus k choose 2 minus k choose 3 and so on. This is just a binomial expansion of 1 minus 1 to the k, where k we said is the size of AF. Okay? And so that's just 0 to the k. Which is 0. Okay? So that proves that nu really satisfies the defining property of mu, and therefore nu is equal to mu. Okay? Okay. Does that make sense? Do you guys have any questions about it? Okay. Let's think about something for a second. Where did I use in this proof that f was not minimal? Why wouldn't the same proof work for a minimal element f? You'll notice that all the steps work except for one step, which is this last step, that 0 to the k is 0. What happens if f is minimal? In other words, if f is the bottom element here. If f is minimal, then, in other words, f is the full dimensional space. That means that no hyperplanes contain it, which means that this is an empty set. And that means that k is 0, and that means that what we will get here is 0 to the 0. And then it's one of those things. What's 0 to the 0? It's not so clear, but it's not 0. 0 to the 0 is 1.
I just told my students it was indeterminate.
0 to the 0 is not 0 regardless.
That's okay, just don't count.
Yeah. No, I think it actually depends on what you're trying to do. 0 to the 0. The point is that's why this doesn't work. Okay. Because if k is 0, then you get into trouble here, and you have to ask Tristram's class what they think of what to do next. Oh, hold on, I ran out of battery. Okay. Okay. Okay, so that proves this formula for the Möbius function. And from that formula, I can obtain, as an easy corollary, the following formula. This formula is due to Whitney for the characteristic polynomial. And it's given by sum over all subsets of A of -1 to the number of elements in the subset and q to the dimension of the intersection. By the way, I should point out that I'm using notation here in a way that I think you understood, but I should probably say it explicitly, because this symbol doesn't really mean anything, as far as we know. The intersection of B. When I write this, what I what I really mean, and this is the definition, is you intersect the hyperplanes in B. So really what I mean by this is you take the intersection over the hyperplanes in B of the hyperplane. So this is my lazy notation for it. It's not just my notation, but it's the lazy notation for it. Well, again, this is just a matter of, I mean, this is really a straightforward corollary because you just plug in. So by the definition, this is sum over f in the lattice of flats of mu of f q to the dimension of f. Okay? And then you say sum. The thing is that now we have this formula for mu of f, which is given by this. Right? Just by using the lemma. And then you'll see that it's just a matter of notation to see that this is equal to this, because here I'm adding over all the subsets of A. And here I'm kind of pre-classifying according to what the intersection of B is. So I'm saying sum over the F's, and then do this over the B's which intersected give you F, and then do this. But instead I could just kind of forget about this pre-classification into different F's, and just sum over all the B's in A, and just make sure that here I say what F really is, and F is the intersection of B. Okay? So these things are equal to each other just by kind of notational nonsense. Okay. So I should say that this formula of Whitney is sometimes quite useful, because like we mentioned last time, this Möbius function is a little bit hard to get a hold of, and the lattice of flats is kind of a tricky indexing set. And here we're getting just a sum over subset, so this is a more manageable indexing set, and then the summons are also more manageable. Okay. One thing you should realize, though, I mean, let's look at the two formulas and kind of weigh the advantages and disadvantages. So we have these two formulas, and like I'm saying here, both the indexing set and the summand are more complicated a little bit. So that gives this a disadvantage. Okay. But the counterpart is that the advantage of this is that this is a much shorter formula. Okay. Because, for example, here this formula has 10 terms, whereas if you were to do it over all subsets of the set, you would have 16 terms. Well, that's not so dramatic in this example, but in general, if you have 10 hyperplanes, you're going to be adding over 2 to the 10 things here, 1,024 things, and this is a huge sum. And in bigger examples, it just turns out that this is much smaller. At least in practice, it is often much smaller than that. Okay, so that's motivation for learning how to deal with these things. And basically, in different situations, you can use one or the other, and to your advantage. Okay. Okay. But now we're going to use this one. So we're going to use this one to prove an important theorem, which is that you can obtain the characteristic polynomial recursively. And remember, we talked about how you can do induction with hyperplane arrangements. The way you do it is through this process of deletion and contraction. Right? And it turns out that the characteristic polynomial can be computed beautifully in terms of deletion and contraction. Like this. Okay? It's just the polynomial of the deletion minus the polynomial of the contraction. This is called the deletion-contraction formula. And maybe I should make sure that you remember how deletion and contraction work. So let's just do it. Let's do it in this example. So, for example, let's delete 3. And there's no particular reason why I'm choosing 3. I could choose any of them, okay? But let's delete 3 because I said so, and then we just get the same arrangement, except that you forget that hyperplane 3 exists. Okay? So you get this arrangement. Okay? And maybe it's a little bit easier to see it if I just kind of erase this part of the hyperplane and just go like this. It's like 2 walls and a floor. Nothing very exciting about this arrangement. Now, what about the contraction? So remember, in the contraction, what you do is that you look at the intersection of the other hyperplanes with this special hyperplane. And now I'll tell you why I chose 3, because 3 is the one that looks nice and flat. Okay. So how do the hyperplanes look here? Well, the intersection of 1 and 3 is this vertical line. The intersection of 2 and 3 is also that vertical line, so 2 ends up being the same hyperplane. And the intersection of 3 and 4 is the horizontal line, so like this. Okay? And that's the contraction. So deletion, contraction. Okay? So here's the proof. This proof, you'll see, again, I'm not going to do anything very intelligent. It's just kind of a computation where you have to keep track of everything carefully. Okay? So I'm going to use Whitney's formula. And Whitney's formula tells me that I should add up over all subsets of A and do all of this stuff. Okay? But I'm actually going to do this in 2 steps. I'm going to do this first for the subsets containing B, or let's do it first over the ones not containing B. Sorry, the subsets not containing H, and then the subsets containing H. Okay. So these are half of the subsets, and these are the other half. The ones that don't contain, and the ones that contain that special hyperplane H. And then I just do this. And this. Okay. Now, why am I doing this? Because here, if B is a subset of A and it doesn't contain H, that means that B is just a subset of A minus H. Right? A subset of A that doesn't contain H is in A minus H. And I get minus 1 to the B and Q to the dimension of the intersection of B. Okay. So that's the first sum, and I hope you see that I'm right on track, because this thing is exactly the characteristic polynomial of A minus H, which is what I want to get. Right. So the first one is fine. Now, what about the second one? Well, it's a little bit more complicated, but not too bad. So, again, what I can do here is, okay, so if B contains H, then I'm going to go ahead and call it C union H. Okay? If it contains H, then it's H union something. And I'm going to call that something C. And that C is going to be any subset of A that doesn't contain H. Right? Because it doesn't contain H because I just deleted H. Okay. So then, like I said, this first thing this is just the characteristic polynomial of the deletion. Okay? Now, what about the other one? Well, it better be the contraction, right? But let's prove it. Okay. So one thing you'll notice is that there is a, here I need to get a minus and here I have a plus. And there's a very natural way to get a minus out of here, because I have minus 1 to the C union one thing. Okay, so let's just take out that one thing, and then we get minus summation over the subsets of A minus H of minus 1 to the C and Q to the dimension of the intersection of C union H. Okay, so that's the first thing. But now, the other thing that I want to do is the following. Let me, in the contraction, let me put primes on the hyperplanes, so that I remember to distinguish them from the original hyperplanes. Okay, so C is a subset of this bigger arrangement, and now I want to get to the deletion, to the contraction. I'm sorry. So I need to get from here to here, which means that I want to get from 1 to 1 prime and so on. Okay, and the thing is this, that you see, for example, in the right-hand side there, I might have C equal 1 and 2. Okay, so this guy and this guy. And then I get minus 1 squared and Q to the dimension of the intersection of H1 and H2 and H, where H is the special guy that I am deleting and contracting, which in this case is H3, right? Maybe I'll use a different color so that you remember that it's a different hyperplane. This is our special hyperplane. that we're deleting and contracting. Okay? But now, what I want to do is that I want to point out that this is the same thing as doing the following thing. I can write this intersection as H1 intersect H3 intersect H2 intersect H3. Which may seem a little bit silly at first. Right? I mean, what am I doing here? Well, H3 is equal to H3 intersect H3. And then I'm kind of moving things around and I get that it's the same thing. So it might seem kind of pointless at first, but it's not pointless because the point is that H1 intersect H3 is precisely 1 prime. And H2 intersect H3 is exactly H2 prime. And so that's how I get to my lower arrangement. Okay. So this is equal to minus 1 squared times q to the dimension of H1 prime intersect H2 prime. Okay. And so basically I can do exactly the same thing in general by saying for each C in the arrangement, which is not the special hyperplane, let's let C prime be C intersect H. Okay, so just like I did over there. And if I have a subset of the arrangement, then, and that subset doesn't contain H, then let's define C prime to be basically what you obtain by priming everything, intersecting everything with H. Okay. Then what I have here is that I can write the intersection of C union H as the intersection over C in the set C of C intersect H. Okay. Let me be very clear. What I'm doing here is just doing in symbols what I did there in that example. Okay, I just need to get the symbols right, but I'm doing nothing new. Okay. Now, this is what I already had minus. Now I get minus 1 to the C. And then here what I get is that this is the intersection. These are the C primes. And so this is just the intersection of C prime. Okay? And now the point is that, well, C and C prime have the same size, so I might as well just prime this thing. And instead of summing over C, which are subsets of A minus H, I can sum over C prime, which is a subset of A contract H. Okay. And then what I get is precisely what I want. This thing, again by Whitney's theorem, is the characteristic polynomial of the contraction. Okay? And that completes the proof. Okay? So that's deletion contraction. And having deletion contraction at hand, it's now very easy to prove Saslavsky's theorem. And the reason for that is that the place where we saw deletion contraction before is that we said that the number of regions satisfies a very similar formula. Only difference being that you have a plus. And similarly for B. We saw that for B it's similar but a tiny bit more complicated. You can look at your notes to see what I mean by that. But then basically, given that the regions satisfy this recurrence and that the characteristic polynomial satisfies this recurrence, then this must be just a matter of doing a straightforward induction. So that's what we do. We just induct on the number of hyperplanes of A. So let me say, I'm going to do it for, I'm going to prove Saslavsky for the regions, and for the boundary regions, it's basically the same thing. Okay. And we're going to do it by induction. So base case is that there are no, so we're going to induct on the number of hyperplanes. So what if you have no hyperplanes? If you have no hyperplanes, then how many regions do you have? Well, just one, right? Which is the whole space. And what is the characteristic polynomial of an arrangement with no hyperplanes? It's actually a little bit tricky, but it's not too bad. So what is, because it takes several steps, right? So how do you get the characteristic polynomial? First, you need to say what the intersection poset is. So what is the intersection poset of an empty arrangement? It's not quite the empty set. It has a unique point, which is the intersection of the empty set. Remember that in every intersection poset, we have a bottom element, which is when you intersect no hyperplanes. And that's the full space. And even if you have no hyperplanes available, you're allowed to not intersect any of the hyperplanes. And actually, that's the only thing you can do since you don't have hyperplanes available. So that means that the lattice of flats, I keep saying lattice of flats because that's a synonym, by the way. So lattice of flats is the same thing as intersection lattice. It just looks like this. It has a single element, which is the full space, R to the D. So that means that what's the Möbius function? Well, it's just 1, right? And so what's the characteristic polynomial? It's Q to the D, right? Because you put these numbers with their dimension. Q to the dimension, and this thing is d-dimensional. So you get Q to the D. Okay? So when you plug in -1, you get -1 to the D, which is almost the number of regions, but it's off by the sign. And the correction factor to get the right sign is -1 to the D. Right, so let's put that -1 to the D. -1 to the D times this is -1 to the D times -1 to the D, which is 1. And so that checks out fine. Okay, so the base case is fine. And for the inductive step, this is one of those proofs where the base case is harder than the inductive step. Because for the inductive step, you just suppose true for arrangements of less than k hyperplanes. and prove it for an arrangement with k hyperplanes, and then what you do is you say, okay, well, the number of regions of A by deletion contraction is the number of regions of the deletion plus the contraction. And because A has k hyperplanes, that means that this has k minus 1 hyperplanes and this has k minus 1 hyperplanes. So you can apply the inductive hypothesis. And that tells you that this is minus 1 to the dimension and the characteristic polynomial at minus 1. And here this is the dimension that A minus H lives in. It's d-dimensional. Plus this thing, what dimension does the contraction live in? Well, remember, when you contract, you lose a dimension. So you get minus 1 to the d minus 1 and chi of the contraction. Okay? So what you get is minus 1 to the d times this minus this. And by deletion contraction, this is what we want. And that's the end of the proof. Okay? That's the end of the proof. And like I said, for the boundary regions, it's similar. So that's great. That tells us that if you want to compute regions and boundary regions, then it's very easy as long as you know how to compute the characteristic polynomial. And so what we're going to do after break is that we're going to discuss how it is that you could actually compute this characteristic polynomial. And there's some very nice methods for doing it. And then once we get really good at computing these guys, we're going to be able to compute regions of arrangements.